Okay. Um, I'm thinking start off with this day 10, and you can already see that I need to make my audio asynchronous. Yeah. And need to do a bit of refactor. So I'll start off with this and then go from there.
The recording here. All right, hello everyone, and welcome to day 10 of Handmade Hero. We have made it through 10 days already. If you are following along at home with the source code from the pre-order, you will want to unzip source 9, source 009 from that zip file, because we are starting with source 9 here on day 10, and you can follow along. All right, welcome to Handmade Hero, the only show currently in existence that I know of in the whole universe where we code an entire game from scratch using nothing but our bare hands, our bare mitts. I know it sounds improbable, but we are going to do it, and we have been doing it, and everyone following at home has been doing it, and it has been fabulous so far. I see no reason to stop now. Now, hopefully, during the sort of warm up to the stream when the little countdown timer was on there, for those of you who joined a little early, you noticed that I conspicuously left a particular page here up for you to read. I don't know if you did. It's a little like summer reading assignment kind of a thing. Only by summer I mean the 20 minutes before the stream started. But what you can see here is the first time I've actually pulled this up. It's a great reference to be aware of. Now it's a little opaque, it's true, but I love having it around. I keep a copy on my machine at all times. It is called the Intel Architecture Reference Manual, and you can find it online just by searching on the Google. If you go in here and you put Intel Architecture Reference Manual into the search box, you will get a link that basically has some kind of long-winded way that you gotta fill some stuff out, but I don't even remember how this all works. But you can eventually get to download, I think it's this thing right here, that's a PDF or something, and then when you open it, you get this nice thing, and it's some kind of long-winded way that you gotta fill some stuff out, but I don't even remember how this all works. But you can eventually get to download, I think it's this thing right here.
What is it again? Combine volume set. One A, is that one? 3C, yeah.
That's a PDF or something, and then when you open it, you get this nice thing. And what this is basically a manual that Intel puts out that really meticulously goes over all of the details of their processor. And you can look over here kind of in the table of contents. Basically this volume 2 one is the one that we're mostly concerned about, but the volume 1 and volume 3 are actually interesting to look through as well. They've got all kinds of stuff about like how the virtual memory works and how the various virtualization features work and how systems programming works, all of this stuff. There's all kinds of good stuff in here that you can read to familiarize yourself with x86 and x64 processor technology and how it works. But in here, volume 2, the most important part for any programmer who's just curious about how the CPU works, there's basically these two chapters, chapter 3 and chapter 4, which have an alphabetic list of all of the actual instructions that you can execute on an x64 processor. Absolutely every last one of them, I think, is in here. And so you can go through, and if you want to know something when you're looking at an assembly code, or you're just curious about what the processor can do, you want to know something, you can go in here and say, oh, we saw that MOV instruction on the stream, well, what's that? And they'll list every possible way that it can work, right? It'll have comments that kind of tell you what goes on when it actually occurs, and it'll have like sort of some pseudocode that says what the processor is actually doing internally. So it's pretty darn cool, and it's something that you should probably be familiar with if you're just trying to educate yourself a little bit about the specifics of how the computer works, which is one of the things that we try to focus on here. So the instruction that I had up was called RDTSC. Some of you may be familiar with it. What RDTSC is it's basically a way of getting at a register, or I mean, it's really a performance counter, but it's basically getting at a thing inside the CPU that increments by 1 every time the CPU effectively like retires a clock cycle. So you know when you say that this is a 3.2 gigahertz processor, well that means 3.2 billion cycles per second that the processor is executing. Each one of those cycles, this magical counter goes up by 1. And the RDTSC instruction lets you actually access the value of that counter at any given time. And the reason that I wanted to introduce this today was basically because we are going to look at some ways of figuring out what time it is in our code today. That's the thing that we're going to be working on. And this is a pretty important way that you can get that information, because RDTSC basically tells you the cycle count at any point in your program. So by asking for the cycle count before you do something and asking for the cycle count after, it gives you a pretty good idea of how many processor cycles have elapsed during the thing that you did. So if you want to know how many cycles it took to execute a particular piece of code, read timestamp counter can give you a pretty good idea. Now, it's not always perfect because there's a number of factors that come into play. The first factor is that not all operating systems save and restore the timestamp counter across task switches. So if your process is running and you're trying to time it, so you do an RDTSC at the beginning and RDTSC at the end, you're going to compare them, you won't necessarily know if the operating system woke up in the middle of that, swapped out your code, ran some other code, and then on the same processor, and then swapped in your code again for the ending RDTSC. So when you do those RDTSCs, you have to be aware that you're timing everything that the processor did in between those 2 points, not just the thing your code may have done. Now, this is, like I said, dependent on the operating system. Some operating systems actually try to save and restore the RDTSC depending on how you access it. We'll kind of look at that a little bit later. There's basically like a query cycle. There's actually a call in Windows you can use. I think it's supported on Windows 7. Pretty sure. There's a call you can use in Windows that basically says, I want to know just for my thread, like just for this particular stream of execution, and that will prevent that particular problem from happening. But point being, things like that can happen. Other things that can happen is you don't actually necessarily know where those cycles are coming from. They don't mean instructions, they mean cycles. So depending on how warm the cache was, how much time it took to get memory, all these sorts of things, the RDTSC numbers are not going to be the same all the time. They're going to be widely varied. So you time a particular piece of code once, you're going to get one value. You time it again, even immediately thereafter, you're going to get different values because maybe things were in the cache that weren't before, all other sorts of things. So it's not foolproof. It's not a thing that magically tells you exactly what the performance of a piece of code is, but it is a thing that gets you some pretty raw statistics on exactly how many cycles elapsed between 2 points, and that is quite useful. So we will be showing how to use it. I just wanted to caveat it there at the beginning so that people wouldn't think it was too perfect. So that's the first thing we're going to talk about today in terms of timing. And we're also, well, I don't know if that's the first one. We're going to talk about 2 things today. The other one we're going to talk about is query performance counter. This is another way of figuring out what time it is, essentially. Again, this is all about clocking. Basically what this is a way of asking Windows and saying, hey, to the best of your knowledge, what is an actual wall clock time? So this is the processor cycle, and it's in terms of the processor's view of time. And what that means is that if we're counting cycles on the processor, we have no idea how that actually corresponds to wall clock time at all. When I say wall clock time, I literally mean like time out in the real world, the real time that you and I experience. Processor time does not work that way. processors these days, depending on the processor, in desktop processors less so, but still, but in mobile processors by definitely, they do a lot of clocking, changes in the clock speed to work around battery life and also to manage heat signatures even sometimes. So like, for example, if only one core is running, they may boost the frequency of that core, but if multiple cores are running, they might drop it, things like this. They'll drop the clock speed of a core when not much is going on to save battery life in a laptop. All of these sorts of things happen now on mainstream processors, which means that when you look at the cycle count, there is no constant meaning for how long that cycle may have taken in the real world. Because for some number of cycles, when you are using this RDTSC, you take your RDTSC at the beginning, you take it at the end of an area, you don't even know if the processor was executing at the same clock rate that entire time. It may be that somewhere in the middle of there, the processor downclocked itself or upclocked itself, and so the first set of cycles, each cycle took a certain amount of time, and then the second half of the thing, each cycle took longer or shorter than the ones in the beginning. So cycles really just tells you something about how much work the processor did in some sense, but it doesn't really tell you about the wall clock time. Query performance counter is the opposite of that. Query performance counter asks the operating system to please give you a high resolution, meaning so it isn't cycle accurate perhaps, but it is fairly accurate. It's not in seconds and it's not in milliseconds. It's something more granular than milliseconds, hopefully. Excuse me. Because you have to remember, if we're running at 30 frames a second or 60 frames a second, you're talking about things on the order of 16 milliseconds per frame or something like this for 60 frames a second, right? Because if you think about it, if you're in a handy, oops, why couldn't I? There we go. Need my little handy calculator. So if you think about it, if you have 1,000, a millisecond, there's 1,000 milliseconds per second, right? So if we're running at 60 frames a second, that's only going to be 16.66666666 repeating milliseconds that we have to do the work for any given frame. Each frame will be on the screen for, rounded up to 17, I suppose, somewhere between 16 and 17 milliseconds. Each frame will only be on the screen for that amount of time, and so that's the amount of time we have to do the work for the next frame. So if we're trying to figure out how much performance, how a particular piece of code gets improved or pessimized by a particular code change, and we're trying to time it, we in general need things that are going to be a lot more accurate than, say, a millisecond, because we only have 16 total of those roughly per frame anyway. So if it was on the order of a millisecond, even if we sped up a particular function by 20%, we would still get the same time back potentially. It'd still be like, well, it took 2 milliseconds, then we sped it up by 20%, and it's like, yeah, it still took 2 milliseconds. It's like, no, okay, we need much more granular than that. So hopefully all these timers that we use are more than that. Certainly cycles is way more granular than that, because there's 3.2 billion of those per second when the processor is running at full speed, let's say. But query performance counter is also going to be more granular than that. It's just not perhaps going to be quite as granular as a cycle count. But it is basically an attempt by the operating system to use some aspects of the system. I think it used to use some kind of bus clocking or something. I don't even know what it uses these days. I'm sorry, I have absolutely no idea. I've never even looked into it on a modern computer. But it basically uses some aspects of the system, whatever it can, to give you back some wall clock time. And you can see here that it's suggesting that its resolution is actually better than 1 microsecond, right? So that's much better than a millisecond, right? Just to give you something, millisecond per, microseconds per millisecond there. So you can see that basically you've essentially got something greater than 1,000 of those per millisecond. We don't actually know because it just says greater than. So it's something in this ballpark. So that's, in theory, going to be pretty high resolution for us to time things with. But the important part about this, as opposed to the cycle count, is query performance counter actually corresponds to wall clock time. Meaning when we look at two query performance counter times and we look at the difference between them, we will be able to actually correlate that out to a real world time. And that's important because it helps with your intuition. If we know that we have 16 milliseconds per frame to do something, it helps us to kind of know how much actual time is this particular piece of code taking. And we think about it, we're like, okay, it takes 0.5 milliseconds. So I roughly know I could do, 30 some odd of them, 30 something of them per frame. I kind of get sort of this idea of that, right? Where again, with the cycles, since they vary so much, it's harder for us to tie that back to a time. We always can, right? We always could actually try to time the RTSCs with the query performance counter, so we know how many roughly the CPU is executing every frame, and then back out those times and stuff like that. But really, without query performance counter, we'd never have a way on a running machine of really even knowing how those RTSCs map back to wall clock time, because we never would have any idea how fast the processor was actually running. We always at least need something that can tell us when a second went by, let's say, so that we could see, using RTSC, how many cycles the processor had actually executed in that second, right? And so that's really where this comes in. So those are the two things that we're going to be talking about today, and I'm just going to show you a little bit about how you use them, and this will give us a little more insight as well into how our code that we've already written is even working. Because right now we don't even know, for example, how fast our program is running. We have no idea how many frames per second we're even getting, right? And this will finally let us kind of get that information. Okay, so I'm going to go ahead here and open up our command prompt. I'm going to get into Emacs, everyone's favorite editor. Excuse me. Still getting over the cold. Feeling better today, but still throat's a little scratchy. All right, so basically what I want to do here is I want to just start by doing something extremely, extremely simple. I want to start by saying, well, we have a loop, right? Here is our loop. We're gonna have a while loop where we just run and our game is sitting in this loop. I just want to start by going, let's print out some number that we can use to sort of see how long it took us to generate a frame, right? And in order to do that, I'm going to use this query performance counter thing because I want to know the actual wall clock time. I want to know how many actual seconds, and it's going to be fractional, it took to generate this. Or maybe we'll do how many milliseconds to make it a little easier to understand printout-wise, so it's not 0.00 whatever. Who knows? But when we get to our actual output debug string, we will actually, excuse me, print this out. Okay, so we have query performance counter. We're going to go ahead and get that. And we're going to call that. Now, the way that it works is it's another one of these Windows functions. You've seen them a lot here, where basically they take something to fill out. In this case, a large integer. So basically, we need a large integer, and we're going to call this begin counter. And we're going to take the address of that. And basically, we pass an address in, and it fills it out. Now, a large integer, I don't know where, I guess there's no way to quick jump to it. I was going to show you the structure of it here, so I'll just cut and paste it into the search box. I want to actually show you the layout. There it is. So basically, a large integer uses something called a union, which we really have not covered in this at all. It's a very simple concept. Basically, what a union is it's just a number of things that are overlaid on top of each other in memory. So it's basically telling you that you can access the same piece of memory in multiple ways. So when you say union in C or C++, you then list things, and each thing listed in the union occupies the same space in memory. So basically, this struct, and this long, which is long is Windows' way of saying uint64, basically, or int64, I should say, since it's not ulong. A 64-bit integer. Each one of these, right, is actually 64 bits, right? That's 32 bits, 32 bits. That's 32 bits, 32 bits, and this is 64 bits. Basically, this union is just 64 bits long, but you can access it using any of these methods. You can say .quadpart to access it as 64 bits. You can say .lowpart to access it as the low 32, or .highpart to access it as the high 32. You can also use .u.lowpart and .u.highpart. Now, why they wanted to do it this way, I don't know. This is called an anonymous structure, which means that these are directly accessible off of the thing. So basically, anonymous lets you access them directly. So I can just say dot low part, right, like that, just with one dot. That directly accesses this. That's why it's called anonymous. There is no actual, it's not actually in here as a separate member. This U right here means that there's basically a field called U inside here that is this, the type is this structure. So if I wanted to access it through that, I would do .u.lowPart, like that. Now I have no idea why they have both of these in there. It doesn't seem like you would need them. They're both, like I said, they're occupying the exact same memory. So it's basically just to allow you to do that or that. So I have to assume that that's just for backwards compatibility purposes, like they made this one originally and then we're like, we should probably do it this way as well or something. I don't really know. But point being, you don't even have to worry about that. It's completely, it's some kind of weird anachronism, I would suspect. Since we are on a 64-bit architecture, we're just going to go straight for the quad part. The quad part is basically the part we want, so we're going to look at that. The quad part tells us basically whatever this value is, and we don't really know how to interpret this value. It's some 64-bit value that is a clock value that we know somehow corresponds to wall clock time. And now we know that begin counter.quadPart is that timestamp, that value at the time that we start the loop. So as soon as we ask for this, we basically now have that start time is in begin counter quad part, right? So then what we're going to do is we're going to jump down. Well, actually, I guess we don't. We don't even need to do that. We're going to do it right here, basically, right? So we're also going to say last counter, right? And we're going to ask for that up here. Excuse me. I figured this was a better way to structure this. I'll tell you why in 1 second, why I felt like that was a good idea. So basically, what we're going to do is we're going to say, all right, at the beginning, we're going to snap whatever the value is. Then we're going to go through the loop, and every time through the loop when we get to the end, we're going to look at what this is, and we'll call this end counter, right? End counter will give us another timestamp, and that timestamp will be how, after we've done everything, essentially, right? And then we'll go back down through the loop, and we'll get to end counter, and we'll get it again. So all we're going to do is every time after we actually print out here, right, we're going to actually display the value here. We're just going to say that the last counter, whatever that is, equals the end counter, right? So we're going to actually store whatever the value was here back into last counter. That will let us essentially compute the difference every time. Whatever end counter dot quad part minus last counter dot quad part, right? If I do this. And I'm going to put this in an int64, and this was the difference, time difference, right? You could say this was the time elapsed, basically. Maybe I should say counter elapsed. Excuse me. If you look at this, man, it is going to be so good to do this stream. I'm not sick. I've done almost the entire Handmade Hero sick. And it's really annoying. All right. It interrupts me. Anyway, so basically all we're doing here is we're saying, well, we have this clock. We're going to look at the clock before we enter our loop, right? Right before we enter it, let's say. We're going to do everything in the loop. We're going to look at the clock again. So we've looked at the clock twice. And just like in the real world, we can now take those two times, the beginning and the end that we looked at the clock, subtract the times, and we will get how much time elapsed, right, by that clock. So then, in order to make sure that works again for the next frame, we will pretend that now, that original clock we took, that's just the new clock value that we got back. So that the next time we get back down here, we'll be differencing it from itself. We'll be differencing it from the last time it passed this point. And the reason that I wanted to do that, instead of putting a begin counter at the top of the while loop and an end counter at the end, is because, well, technically that doesn't quite capture all the time, right? If the actual act of getting back to the top of this loop, maybe the process got switched out or something happened that took a lot more time than just doing one comp and a jump to get back to the top, we'd miss that time. So I want something that's guaranteed to never miss any time. So by always using a single stable place where we check the clock and differencing it from that every time, we know that we've never had anything escape our time window. Our time window is all inclusive. There's nothing that could have happened that isn't accounted for within our clock window. So once we do that, we have a counter elapsed value that basically tells us how much time has elapsed. Unfortunately, we still don't know how to interpret this clock value. So if we want to print out how many seconds something took, how many milliseconds something took, we don't know. What we'd like to do is we'd like to be able to translate this back to human readable wall clock time instead of machine readable clock time, which we don't even know what it is because we don't know how Windows is even arriving at these clock values. But fortunately, they give us something that does exactly that. It's called query performance frequency. Now, what query performance frequency does is it basically tells us how many increments this clock goes through in 1 second, right? So basically, if we just ask for this up here, right, if we say, hey, query performance frequency. Now, the question, I think, I'm going to double check this. I think we can just ask for this once because I don't think query performance frequency is allowed to change. But let me see if they actually say that for certain somewhere. Let's take a look. Yes. The frequency of the performance counter is fixed at system boot time as it is consistent across all processors. Therefore, the frequency need only be queried upon application initialization and the result can be cached. So at least according to the documentation, which granted is sometimes wrong, we only actually have to ask once. So we can just say the performance frequency,
Excuse me.
or maybe I'll say the perf counter frequency, right, is going to be something we can just ask for. We then know how many of them happen per second, right? And we are good to go. So there we go. We now have that value, and we can use it. So if we actually go ahead and get that, right? Excuse me. I'm going to put this up here in the area. If we do that, we can then come down here and say, well, we have a counter value that elapsed. And we also know how many of those per second we're actually doing, right? We know that basically up here, in fact, I could even stuff this into a more useful variable. I could say int64 perf count frequency like this, and say that that was perf count frequency dot quad part like we did before, and this will be just a thing that uses to hold that value coming back. There we go. So now we have the perf count frequency. We know that is how many counts per second that thing is doing. So in here, when we have the counter elapsed, we can actually say, well, however many frequency,
Missed it.
just a thing that uses to hold that value coming back. There we go. So now we have the perf count frequency. We know that is how many counts per second that thing is doing. So in here, when we have the counter elapsed, we can actually say, well, however many elapsed, right, divided by how many per second there were, that's how many, that's how many seconds actually elapsed. I just spilled my coffee, ladies and gentlemen. It was bound to happen eventually. Of course, thankfully, it kind of landed on my mitten, so it did not actually spill anywhere, but it almost did, and it almost wasted valuable coffee, which is really a crime. So doing this divide, saying the counter counts that we saw divided by the frequency of that counter gives us the seconds. And of course, one thing I should mention for the benefit of those of you who are maybe not math stars, I know I am certainly not a math star, so I just want to point this out for people who don't think about things this way to maybe get you thinking about things in this way and doing a little more reading in this area perhaps. One thing I wanted to point out is dimensional analysis is particularly useful when you're doing these sorts of things, you know, in your head when you're writing this sort of code, just something to think about. If you have something like a counter and you say, well, I have a counter value and I know it came back, it was like X number of counts, right? Which is what we have. Like we got this back and we know that this is the number of counts that transpired, the number of like clocks that transpired, right? Number of counts, number of counter increments. And then we also know that this performance frequency thing, when we read the documentation, right, it says counts per second, right? So we also have a value that is counts, right, per second. So if you have two values, one that is counts and one that is counts per second, and you want to know how many seconds something took, which is this, right? But you have a value that's how many counts it took. The question becomes, how do you get that value, right? And the answer is you can always just look at how the units cancel on the divide. So let's say we were to multiply these two things together, right? What would we get? Well, just look at what happens with the units. Counts, this is essentially over 1, right? This is x counts and counts per second, right? If I multiply these together, I would get counts squared, right? Counts times counts over seconds, right? That is completely useless. That is not, count squared over seconds is, we don't even know what that is, right? So what you want to do is look at how do you actually cancel the counts, right, out like this so that you're just left with seconds, okay? And the way that you do that is you say, well, x counts, I just need this to be inverted. If seconds was on the top and counts was on the bottom, the counts would cancel. And that's what a divide is, right? A divide flips the two things in a ratio. So if I do counts divided by, right, counts per second, that is the same as multiplying by seconds per count, right? So the counts cancel and we're just left with x seconds, which is what I wanted. So looking at things in terms of flipping, basically flipping your ratios by either dividing or multiplying, you can line up a whole string of these things if you've got them and cancel all the things that you actually need, right? It's a standard kind of thing in dimensional analysis to do where you've got some number, like you've got x seconds, and you want to know how many days x seconds is, right? And you can kind of just line things up. You can say, okay, well, at x seconds, I would need to multiply by how many seconds. I need to cancel seconds. So there's seconds, and I can translate seconds. I know how to translate seconds into minutes, right? Because it's basically 60 seconds per, 1 minute, right? And I know how to translate minutes, right, into hours because I know there's 60 of those, right? So I can just say 1 hour is 60 minutes. I know how to translate hours into days because there's 24 hours in 1 day, right? And just by literally going, well, whatever this thing was, I got to put it on the bottom to translate it into something on the top, put it on the bottom, translate something on the top. I made the math exactly what it needs to be. It's just multiply it out. X times 1 times 1 times 1 is x. 60 times 60 times 24. 60 times 60 times 24. These all cancel. Minutes, hours, hours, day, right? And we get this. And that is the answer. So you would just divide x by 60 times 60 times 24, and that is how many days it is. Again, if you're a math-minded fellow, this is trivial. But if you aren't, it's worth starting to think about things like this. There you go. Okay. Let's go back to the actual code, which I have not really been doing anything. Okay, so there's an end counter here, and there's a last counter. We got the frequency here. I got to put that in there. Let's see. Got to take the semicolon there. All right. So basically, this is going to give us back that value, but the question is, what are we going to do with that value? Well, what we can do with that value, certainly, is we can say, well, we've got the counter elapsed divided by the performance frequency. The problem is, if this is an integer divide, right, we know that the perf count frequency is how many counts per second there are, and we know that we probably didn't take a whole second to draw this frame. So this is just going to come out to 0. The integer divide, there's no fractional part, so something that's a large number divided by something that's a smaller number is just going to give us 0. So seconds is not particularly useful. So what we might want to do is say, well, if we multiplied this by 1,000, right, first, that would actually give us milliseconds now. So if we multiply this by 1,000, then we've got some room to do our divide. That would give us how many milliseconds it took to do this frame, right? So this is milliseconds per frame, right? That is the actual value. So now we actually know how many milliseconds per frame we're actually taking, and we can just take a look at how many that actually was. Now, of course, it's going to vary per frame because, like the first frame, we may do a lot of extra work. In the first frame, we may have a lot of Windows messages that come in that are like about initializing the window or something, right? So the first time we do it, we're not necessarily going to know. So we want to actually look possibly at later frames. Okay. So basically what we want to do is print this value out. Obviously, we have output debug string, which we can use, but we don't actually know. We've never actually seen how to print out a value. Well, we're going to look at that in a little more detail when we do the platform independent code. We're going to look at how to do our own output of values. So what we're going to do first is we're going to use Windows' code, much like we used Windows' sign function to just test our stuff. We're
Um, wonder how you do that. Query performance counter. Clock real time. Standard. Standard POSIX. Hey, live on the floor. How you doing? Does it? Yeah, it does that. System times back. What is that? I'm following Handmade Hero. I don't know if you've ever heard of it. It's basically a series by Casey Muratori. Excuse me. I'm following along in Linux and Zig. System dot clock get time. Yeah, more or less, I'd say. But it's also everything around game dev, which is what I find more interesting. What about Jonathan Blow? What are the resolutions for time.timer? What's my view on AI and coding? How you utilize it in your way? I mean, it's It's really good, right? No, I live in Thailand. How do I utilize it? Yeah, I'm from India too. Um, well, I use it quite a few ways. I think the most common way is, well, I don't know. There's quite a few. Um, okay, the first way is to understand something that I don't know. That's like, it doesn't happen that many times, but whenever I'm stuck on something, I find it's great to ask a question and understand. And I also maintain a project. Well, it's like a paid software on my own, and I use AI quite a bit to recreate similar features. I don't know how to explain it. Like I know I have all the components already for that feature, but it needs to be tweaked a little bit. So I do use it quite a lot for my own work, and at work I use it. Um, I use it a lot to convert data types. That's like the most common use case, and sometimes to just write some SQL queries because it's a lot faster than typing it out. Yeah, there's a lot of use cases really. I use it quite a lot. I don't know how what. Well, we can look at the one I'm doing now. Let's say what's the equivalent of window. If I don't understand something sometimes, like a piece of code, um, I'll ask it as well. I mean, I don't know. It's hard to explain. It's quite a few use cases. Standard time. That's it. Okay, yeah. Oh, 6 o'clock get time. Understand the type that it returns. Const time spec is equal to system.time spec. What about clock frequency? Alright, good night. Live on the floor. Must be quite late. The timer struct internally uses. Okay. Okay, this is basically, so I can just use okay, I can use either one of those.
We're going to use Windows' code to output the variable as well. But later on, I want to show you how that works so it's not a mystery to you how you output a number. Because obviously, someone knows how to do it since it works. There is a thing called WSPrintf, which you can use in Windows code to quickly generate strings. And basically, all you have to do to use it is you create some buffer that it can write into, right? You can create some buffer like this. You can basically pass this buffer to WSPrintf. You can then give it some thing that you want to print out and give it the value that you want, and it will do it. Now, the way that it does this is a little wonky, and it's just the way C's standard library originally did it, so it's the way Windows does it now. Basically, what happens is it takes a format string, so it can actually be something like milliseconds per frame, colon. That's going to actually appear in the buffer. It's going to copy those characters to our buffer, right, that we've made here. That's 256 bytes long. It's going to put those in there, but then it's also, excuse me, it's also going to go ahead and look inside the string. It's going to process the string as it goes and look for anything with a percent in it. If it sees a percent, it will use the next thing that comes after it to determine what to print out, okay? And then the parameters that come after it, right, after the comma, it will then use to fill in whatever the percent told it was coming. So if I say something, I want to have, I've got like a thing here, that once this is, we don't actually need 64 bits to store this, so we can actually do something like 32, and I'll tell you why in a second why I do that. %d, for example, is the code that says, hey, this is a 32-bit integer, basically. That's what that does. So this says, well, I'm going to pass a 32-bit integer. Please replace the %d in the string with the 32-bit integer that I point you, right? And we can actually put a little ms after that for milliseconds, let's say. So in here, we can now just pass buffer, and that will actually do the printout for us. Now, there's a bunch of other things I want to talk about here, but I'm just going to see if we got this working first. Oh, I got to actually launch the debugger, of course, before we do anything else. So let's go ahead and do that. Here we go. So I'll close the app. We can kind of see what happened here, right? And much like I said, it's not particularly predictable if you look through here. The first frame was long, like I said it was going to be, not surprising. Then each particular frame you look at took us something on the order of 6 milliseconds, which occasional spikes up to 10 milliseconds. Now, normally those spikes, you know, is that typical on this type of machine? I don't think it probably is, but you have to remember we are on this machine, all of our timings are highly suspect because we have this fine fellow, the open broadcasting software that is allowing me to talk to you on Twitch. You have to remember that it is doing a bunch of work to capture and compress this frame and everything. And even though this machine has an ungodly number of processors, I think I showed this in the intro to C stream. It just has an ungodly number of cores. It's 2-processor machine. Each one has 6 cores or something like this. Or 4 cores and 2 hyperthreads per core. I don't even know. I think it's 4 cores, 2 hyperthreads per core, 2 processors, something like this. I don't even know. We'll have to look it up at some point when we start talking about when we start talking about optimization in terms of processors, we'll start getting into stuff like what a hyperthread is and why you care. But for right now, just to say, there's tons of horsepower on this machine. It shouldn't be a problem. But the point is that is not necessarily the case when multiple people are contending for the same resources. Since we are blitting to the screen, we are copying our image up to the screen, and our runtime includes that effort, that ability to display things on the screen. OBS is trying to capture the screen from Windows. We may run into circumstances, for all I know, where there's like a lockup where we have to wait for it to do something and all. I don't know. I've never done any profiling of code that runs on a machine where video capture is running concurrently. But suffice to say, as we're doing the stream and doing timings, before we start doing any serious performance work, I will probably try to do some kind of outboard capture to get that out of the equation, because all of the timings that I take on this machine are going to be highly suspect until we get OBS out of there so that we know we're doing direct throughing, basically. But point being, what's interesting about this, and what I hope is pretty interesting to you just from looking at this, is this 6 milliseconds here. You remember 16 milliseconds, and I can print out this value as well. I don't particularly love frames per second as a value that's useful, but it helps because people quote it in the news all the time and that sort of stuff. But we can certainly put out that number, how many frames per second there are. So frames per second, right, is going to be the milliseconds per frame computation. Basically, it's going to be the same as that FPS here, right? Well, you know what? You should be able to do this now. You should not need me to do this, because I told you how to do dimensional analysis. So let's see. I'm gonna do this real slow, so that hopefully those of you at home who are going ahead will get it. I want you to get it before I do. Okay?
We have milliseconds for frame, and we need frame. It's milliseconds divided by milliseconds per frame.
So what did I say about dimensional analysis? I said that we want to look at what's on top and bottom of the ratios. So our target, right, is frames per second, okay? And what do we now have?
Okay, it's per second. You know how many... Well, it's one frame for each of the values printed. That's in milliseconds. So you divide that by 60, and you should get your frames per seconds. Kind of, not sure.
Right? What do we actually have? Well, we've got two values we could work with. We have counts, right? We have x counts. We also knew how to translate that to seconds, right? So how do we get from here to here? I want x counts in frames per second, right? Now there's a little bit that I'm not saying yet. So see if you got it. Okay, hint number one.
Well, we know each frame, how much time it takes. So based on the time taken, yeah. Okay. Let me think this through. So we know one frame, how long it takes, and in milliseconds. To get x frames in seconds, so it's seconds divided by milliseconds in seconds. Yeah, I usually do it like, so one frame, let's say x seconds, x frames 1 second, and you just do that.
One is that this isn't just x counts, this is x counts per frame, right? Because that is what we did. We timed one frame. So we know that x counts go by per frame. So counts on the top, frame on the bottom, right? Make sense?
Mm-hmm.
Does everyone have it yet?
Yeah.
I don't know if everyone has it. See, the thing is, you can see me through the webcam, but I can't see you through the webcam, and that's really the problem. So I can't see if you've got it or not. But it's okay. So let's go ahead and take a look at this here. So the first thing that I would say, right, is I want to be able to invert this, right? I need frames to be on the top, right? Because frames is on the bottom at the moment, and that's no good, right? I also know that I want seconds. So really what I could do is I could say, well, first of all, we know counts per second. That was our query performance frequency. So if I multiply this, right? Oops, what's going on? Oh, I accidentally, did I hit some button there? That was interesting. It kind of froze me out, right? So what I want to do is I want to multiply this by something that's got like counts on the bottom, right, and seconds on the top, like this. How many seconds per count, right? And we know that that is basically the inverse of our performance thing. That would give me, because our performance frequency was counts, right? Counts per second. So the inverse of that, which is obviously, and I guess the one thing that I didn't say in that thing was, which is again mathy, so I suppose I should have said it, is that if I have some ratio, 1 over that ratio, like if I do 1 over counts per second, that gives me seconds per count, right? So I can always invert a ratio. I can flip it around by doing 1 divided by the value gives me the inverse of that value, flips the 2, right? So basically the most straightforward way to do this, right, is to say, all right, the first thing I want to do is I want to flip this around, okay? So I'm going to do 1 over this value. I'm going to take 1 divided by our counts per frame, right? And if I do that, then that will give me, I can't figure out how to actually erase this. I'm trying to, but I can't do it, right? Okay, there we go. So if I take 1 over this value, that'll flip it around, and that will give me 1 frame per x counts, right? Then I multiply that by how many counts, right, per second there are, which we know this is our frequency, counts per second. This was the performance frequency, right? And so I cross out my counts, and I'm just left with frames per second, which is what I wanted. So we need to do 1 over our counter, right? We need to do 1 over our counter, that's this step. And then we need to multiply by the frequency, and that should give us our frames per second. Does that make sense? Hopefully that makes some sense. I don't know if it does, but if it does, there you go. So if we have 1 over the counter times the frequency, well, we can just multiply that out. That's just the frequency divided by the counter, right? Now, if you think about that, that makes some pretty good sense. That's basically saying we have, we have our frequency counts per second, our f counts per second, right, over our counts, right? And that just drops out the count values, which is sort of what we wanted. And seconds, of course, moves to the bottom because it's on the bottom. All right. Okay, so basically, dimensional analysis, play around with it. I realize it's hard if you've only seen it for the first time. That's probably not the best explanation anyone's ever given in the world. I can tell you that right now. Like I said, I'm not the math guy. So maybe take a look.
That's pretty good though. Yeah, it makes sense.
Excuse me, online for something like that, or maybe we can find some links to it. But basically, that's all we're trying to do here. So for frames per second, we basically just need to do our seconds per frame. I'm sorry, our what's our performance frequency? There it is. Our counts per second, basically, right? Divided by how many counts we actually had. Oh, there we go. Counter elapsed, right? Like that. And that should give it to us. I'm not sure. Again, like talking on the stream kind of makes. There we go. Okay. And then we close it. And then you can sort of see now this number translated into something that's more like what you would see reported in the press. So 6 milliseconds per frame is 143 frames per second, right? And we can sort of double verify that because if we've already computed the milliseconds that it took, we know there's 1,000 milliseconds in 1 second. So dividing by 6, there's that 166 value. Of course, this is going to be more accurate than that because it's actually a decimal here, 6 point something, something, something. And then there's the 7, which is a little bit lower value. So that is 1,000 divided by 7, and that's up in the 142, which is right accurate. So that was probably almost exactly 7. So that's basically, I mean, that's really all there is to it. This is how you get a counter. There's pretty much, I mean, yeah, I think I've said just about everything there is. Dimensional analysis can come in to help you a little bit if you start getting confused about how to compute a particular thing. You want to look at those units. Try to let the units help you, and that's the way.
Well, let's try and do it. Just get milliseconds. Seems better. I'm gonna have to like stop my music. I mean, I'll leave it on audio because it's not asynchronous yet. The timestamp. Yep. Mm. But what else do I need? Okay, I need FPS. This. Let's also make this insensitive. Frequency. PSP milliseconds is 10 to the power minus 6. Is it? Yeah. I do have FPS. Cap time it took for 1 frame. And if yes, should be. That's the time it took for one frame. Milliseconds. One frame that many. So it should be seconds divided by. Is that time that second? No. Why am I getting stumped as this? Okay, I do have. Right. So it should be. Thousand, that's a microsecond. No, that's a millisecond. Divided by time per frame. Kinda looks right. So that's milliseconds. Milliseconds to seconds is 1,000. Okay, looks right to me. Div. Okay, that looks quite wrong. Unless my CPU is like insanely fast. Why do some of them take so long? Is that even correct? It looks a bit wrong. It looks way too fast. Let me check start time. That milli timestamp. It's also the same. Okay. What I would like to see is first one. Oh, because the sound plays before. Oh, let me just play, but then. Oh no, then it'll play every time. Oh yeah. See what happens if I put this here. So each frame should now take 2 seconds. Is it a second? Not a second. Where's my sound buffer? Sample rate times 2. Yeah, because, okay, it is 1 second. This is channels. Yep. Okay. I mean, that's fine. So it is kind of accurate. Hang on, I'm gonna stop the sound for now. It'll probably be a bit slower. Oh, it slows down when I move it. What happens if it just completely stops? Interesting. Slows down quite a lot when I make the window bigger. This is some random stuff that I printed. You can ignore what you see. So if it was full screen, ooh, that is really slow. Okay, good to know.
Where that goes. Now this sort of thing is highly problematic. There's a number of reasons why this sort of thing is highly problematic. The printout I'm talking about here. There's so many ways that this sort of style of printout can go wrong. The first one is you can pass a buffer that's too small. There's ways of getting around that. Basically, if you go look up in MSDN here, obviously WSPrintf is documented here. There it is. Basically, there's versions of these sorts of things where you can pass in the size of the buffer to prevent it from possibly going over. Basically, I don't know, I guess they have these string CB printf here. Yeah. So basically, they have newer versions which do that, which do it. Here's an easier one to understand. So here's WNSPrintf. WNSPrintf is the same as WSPrintf, but instead of just taking a pointer to a buffer, it takes how long the buffer is as well, right? So instead, you could also point here, you could say size of buffer, like that, and now you know that if you pass in a buffer that's too small, you won't overwrite memory, basically. Because you have to remember, basically, all the original one sees, let's go ahead and, what, WNSPrintf, there, right. Not found. Why are you not found? It's right there. What's the problem? What is the problem? Oh, it's in some special H file. All right. I wonder if this will cause, this may have cause us linked with something special as well, in which case I'm not going to use it. But let's take a look. Yeah. So I'm not actually going to use that. I'm just going to show this old one and say the fact that there is one that takes the size of the buffer. So basically, one of the problems with this thing is you pass it a buffer, but it has no idea how big that buffer is. So if you were to pass it a string that doesn't fit in the buffer, now we know this will always fit in the buffer because the number of the size of these two things can never actually be enough characters to make this get out to 256. So this is perfectly safe. But you could imagine if you made a mistake and you pass a buffer here that isn't big enough to hold the thing you're printing, you just overwrite the end of memory. Because it has no idea how big the buffer is. It assumes you gave it a buffer that was big enough. And if you didn't, off you go. That's definitely a source of bugs right there. Second source of bugs, and sometimes some compilers like LLVM will try to catch these by parsing the string at printout time. Basically, these percentage things are sort of just like assumed to line up with whatever you pass it. And this is basically a thing that does what's called varargs, which says the compiler just sticks whatever you put after the format string here. It just starts sticking these things on the stack, and then this function will just pull things off the stack based on what it sees here. But you could say that there was a ton of stuff that was never actually there, right? And the function has no idea that happened. So it starts reading shit off the. I'm sorry, I'm not supposed to use colorful language. It starts reading stuff off the stack that it was never supposed to look at, that isn't even a variable potentially, that who knows what it is. It can do all sorts of things like that. If I told it that a pointer was coming, %s says that there's going to be a pointer to a string, but I didn't ever pass a pointer to the string, then you get into a thing where you'll do an access violation when it goes to try and read that. So it's fraught with peril. It's definitely fraught with peril. So typically, I don't use this sort of code in anything I'm going to ship. Like, this is not code that I like to see hanging around in like something I'm sending to an end user. I like to write my own versions of these things and know that there's some degree of accuracy to them if possible, and so on. But basically, if there is debug code or profiling code like this that we know is only going to ever really be run on our machines when we're developing it, then you can go to town, because a bug in there doesn't cost you anything. It's like, yeah, you crashed on your machine, or yeah, you had some security exploit on your profiled version. That's not that big of a deal. But if you're going to ship this to an end user, this sort of stuff becomes dicey. It doesn't mean you can't do it. It just means that when you do it, you got to know, you really got to understand what you're doing. You can't just throw it in there and be like, I saw it on Handmade Hero and I just typed it. It's like, no, this can go wrong real quick. So you want to leave this kind of thing basically as debug code for the most part unless you really know what's going on. All right, so the next thing we're going to do is basically all we're going to do is augment that with that RDTSC thing that I talked about, right? So we're basically going to say, all right, when we do this query performance counter, I'm also going to go ahead and snap the RDTSC value. Now, thankfully, we can actually do that right from the compiler. There's usually a intrinsic for it, which I wanted to show you the documentation for. But I don't see. It's usually like underscore RDTSC or something like this that I don't see right now. Why am I not seeing it? Underscore RDTSC. What's going on here, people? There should be an RDTSC. On LLVM, it's that. That's what I used most recently, but let's see. So there it is. Yeah, why didn't it find that? Underscore RDTSC. Oh, I'm so sorry. I forgot that second underscore. It makes all the difference there. Okay, so it looks like that's all there is to it. Yeah, you just get, yeah. All right, so it generates the RDTSC instruction, which returns a processor timestamp. That's exactly what we wanted. We just want to call that function of the processor and get that value back. So basically, we're going to insert another thing here. We're going to say that there's an int64, which is the last timestamp counter from the processor, right? Or we can also say last cycle count, right? And basically, that will just be equal to whatever RDTSC was. And that just full on should output that instruction. Later, when we get down here, we're going to do exactly the same thing as we did before. So now we go to end cycle count, and we get it again. Then when we do our thing, and you know what, I'm going to do that since this is cheaper, RDTSC is cheaper than query performance counter, I'm going to do that one first, because that's going to be the more accurate time there, I guess. Well, it doesn't actually matter because we're doing round trip time, so it doesn't matter. You can put them in either order because it's going to have to then go through this to do the rest of it as well. But point being, so then we're going to actually do here as well, we're going to do cycles elapsed, right? And we do exactly the same thing we did before. We do the end cycle count minus the last cycle count. That gives us that, and we do last cycle count minus, equals end cycle count to set it so that next time through the loop we'll be using the most recent clock value. And then we know how many cycles elapsed it was, so we know the milliseconds per frame, and we also now know, and we can actually get rid of this because we actually said milliseconds per frame and frames per second, right? We're actually pointing out those values. I don't know, I'm not doing a very good job separating these. Let's do comma, comma, and then we want something here that we're going to print out, which is basically our cycles per frame, right, from the processor. And so the cycles elapsed is going to be a lot, right? So maybe what we'd rather do is say like megacycles, right? So maybe we'd rather do something like megahertz, right, like this. So we're going to say basically this is how many megacycles per frame we're actually taking, because otherwise, oops, sorry, that's divide there. So we're actually going to divide that out so that we're not actually looking at such a huge such a huge value. So we're going to say this is megacycles per frame, and we're going to grab this value out here like that. And then we are going to say that this is also casted down to int32. And the reason I'm casting these down to int32s is because %d is kind of a uniform way to print things out, whereas printing out a 64-bit integer using a printf style thing is only very recent. So %d actually always works on every C that you'll ever have, whereas printing out 64-bit can be a little bit dicey depending on the circumstances. So I'm trying to convert these to 32-bit values before I print them out. So hopefully that'll give us what we wanted. We can then go ahead and run this and see if that makes any sense. We'll stop it. And we can basically see here that, in a given frame, we took 6 milliseconds and we executed somewhere around 20 million instructions to do that frame in the 6 milliseconds. Wild. So let's see if that holds water. Basically what we're saying there, again, if we take a look at the divisor, we're basically saying, okay, if we had 152 frames per second, right? So that's how many frames per second we have. So 152 frames a second times the number of instruction megahertz, megacycles, which was 20 there. That should come out to roughly the processor speed, right? And it sort of does, basically. And we don't know what this value's fractional is because we're not printing it out, right? So there we go. We've got that. And if I look at the actual, I don't actually know how to get to this anymore. I always forget. Where is it? If we look at the clock speed, we should see it's like, yeah, okay, so it's roughly around there, right? It's 3.19 gigahertz. And so that's roughly in the ballpark of where it should be. And I think if we did a little more precision there, it should come out. In fact, we could actually do the math with the actual original values and see what it actually was. We could say, for example, we could do the milliseconds per frame times the cycles elapsed or something like that. So basically that there tells us all the clocking information that we want to know, just not to very high precision. So the next question is, could we do fractional? And the answer is yes, we can do fractional. We just have to learn a little more about how you do printfs. Now, if you want to do fractional, you have to use the C runtime library, because if I remember correctly, WSPrintf, the thing that's built into Windows, cannot print out.
Okay, I think it's mostly window-related stuff till the end. Maybe final thoughts?
So that's basically everything about timing. And what you can do now, and this is something that we'll do a bit later when we get to profiling, is in the platform-independent layer of the code, we can also build a little bit of a superstructure that calls into the platform layer, the platform-dependent layer, to get timing information at various points in our code. So we'll be able to see who is taking that time. So we timed the whole thing, right? But you could imagine us doing something a little bit different, where, for example, we could query the performance counter right here as well, right? We could say, let's take another performance sample right here called mid counter, right? Like this. And we could take a look at how long it took us to do everything but that stretch dibits, right? This is where the stretch di bits happens. How long does it take to do everything up to that point, right? You could do that, and you could come in here and say, well, the amount of counter elapsed, we could do the exact same thing and see how long that takes. That is the kind of thing that we'll be doing when we get into profiling. We'll have some nice utility function we can call to just drop stuff into our code and see how long every individual thing takes. How long is stretch dibits? How long does it take us to build our gradient? How long does it take to fill the sound buffer? Those are all the sort of things we'll look at when we actually start to look at profiling. But that's really all there was to it. Now that you have those tools, you can build any kind of profiler you want. We'll see, some interesting tricks for doing that. But that's it. So anyway, we've come to the end of the stream, and it is time for Q&A. Thank you so much, everyone, for joining me for another Handmade Hero. I hope that that was all relatively clear. I know it can be kind of confusing with all these sorts of things. Hopefully the clocking stuff was clear. This guy, like I said, this is a whole topic unto itself, these printfs. So if you're a little hazy on that, I don't blame you. Like I said, I don't really want to harp on it. It's basically just a simple way you can use to print stuff out. Any tutorial you read online about how to use printf, and basically there's a bunch of variants.
One thing I did want to check was, how can I call DTSC within the Okay, I gotta inline some assembly. Yes, that sounds pretty cool, to be fair. Never written assembly. Okay, I think I'll add it to do. The to-do list is growing quite high. What's the word? Can I link it to PDF? Never mind. Yeah, I want to try if I can read this and create the method. We'll see. See. To get cycles. Per frame. Okay, so the biggest to do is, where's my sync? Yeah. So it's making, so this one's using a simple synchronous API to play sound. But this is not, I can't use this because I can't block, what's the word? Yeah, the main loop every time I need to play audio. So yeah, so the first thing to do tomorrow is to change this to a sync. And plus this one sounds quite a lot of fun. Leave it to do list here. 26. And move sound buffer. Okay, I'll do a bit of cleanup because there's like constants everywhere. And there's a lot of to-do comments. So I'll do that tomorrow before I move to day 10. What is day 10? Basics of platform API design. Sounds interesting too. Alright, that's for tomorrow. Anyway, thank you for hanging out. It's a bit of a short one. I wasn't gonna stream today. I was like, what the hell? Okay, I think that's it for today. I hope you have a good one. Shall see you back here